For today's lesson, our focus standard comes from Grade 8 Expressions and Equations, Standard 3. Use numbers expressed in scientific notation to express very large or small quantities, and to express how many times as much one is than another. So our topic today is the first lesson in scientific notation, and we're going to talk about magnitude as powers of 10. Our essential question today is, how does magnitude as powers of 10 help us comprehend very large or small values? So take a moment to copy this into your header along with today's date, set up your question column, and your note column. So in order to start to understand scientific notation and why we use it, we have to understand magnitude. Magnitude is something that we use. Well, let's just go ahead and get started here. Magnitude is something that helps us describe how big or small something is, expressed in the smallest power of 10 that exceeds it. So you might be wondering, okay, what does all that mean? Well, powers of 10, we have a base 10 system, meaning we use numbers 0 through 9 to represent all of our numbers. And so it talks to us about, well, how many place values is that? And that is going to be our magnitude. So as I said here, every place value is one power of 10 because we're a base 10 system. And we're going to need to rely on our use of the laws of exponents, which we've been working on for the previous set of lessons. And remember that positive powers equal large numbers, and negative powers are decimal or fractional numbers. We talked about as repeated division. Well, if you repeatedly divide something, you're going to get a really small decimal or fractional value. And then thirdly, we're going to jump right into some crazy facts. So these are facts I found by doing a little bit of research to practice comprehending magnitude and understanding, well, how many powers of 10 is that value? So here's our first one. The Huffington Post published an article in 2012 that is claiming that the average person blinks 28,800 times a day. So while this number is something that we might be able to relate to, okay, it is a big number, it's in the 10,000s, we're going to practice here. So we want to determine what is the magnitude of 28,800. So we're looking for the smallest power of 10 that exceeds it. So in other words, how many place values? So it's going to be represented as a power of 10. And if I put my cursor here, we can see that there's 1, 2, 3, skip over the comma, 4, 5 place values. So the magnitude of 28,800 is 10 to the 5th power. And 10 to the 5th power, if we multiply 10 times itself repeatedly 5 times, is going to be 100,000. So start to look at this number in comparison to this number, because it's going to come in handy. Alright, let's take another shot at another crazy fact and understand it in terms of magnitude. According to the National Oceanic and Atmospheric Administration, referred to as NOAA, the Earth's oceans hold about 352 quintillion, 670 quadrillion gallons of water. So think about maybe a gallon milk jug. All of the water in our oceans being 352 quintillion, 670 quadrillion gallons of water. So this is starting to get into a number with a lot bigger magnitude. We want to be able to kind of wrap our head around it. So we're using place value, expressed as powers of 10. So how many place values are there? Well, I'm not going to move my cursor for each one. We use commas for a reason to help us see it in chunks of 3. So let's count by 3s. We have 3, 6, 9, 12, 15, 18, 21. So counting by threes, seeing all those sections, I counted 21 place values. So magnitude expressed as powers of 10. What do you think it's going to be? Let's see how you did. 10 to the 21st power. Which puts us here. And we're getting into place values so large that I definitely have not remembered the place value past quintillion. It would be the version of 6 million billion things. So, starting to understand why we might want to use place values. I know that you guys are like, oh, she's really going to make me write all those zeros. Yes, please write all those zeros. So the magnitude of the amount of water that can be held in the Earth's oceans is 10 to the 21st power. So far, our first two examples have us in the positive powers of 10. Meaning that we're talking about very large numbers. So let's take a look at a couple that are smaller numbers. Here's our next fact. According to the YouTube channel I found, How Much Things Weigh, a single standard square post-it note weighs 0 and 15 thousandths of an ounce. So, what's the magnitude? Now that we're talking about a number much smaller, less than 1, this should be an indicator that we're going to use a negative power of 10. We're talking about smaller numbers. And so, we have to look up here at our notes again and say, well, we're looking for it of magnitude expressed in the smallest power of 10 that it exceeds it. So this might be a little counterintuitive, but let's think a little more about place value. Here's our decimal point. The further away to the right, the further behind our decimal point that we get, the smaller the value. And the closer we get, the greater. So I need to find where can I place a 1 behind the decimal point that is going to be the smallest power of 10 without going over it. Well, right here in the tens place, I'm going to have 0, and I think I even have it written here. 0 and 1/10 is the decimal that is expressed as tenths or a power of 10. That's going to exceed this, because if I use 0 and 1/100th, 15 thousandths is still bigger than 1/100th. So 0 and 1/10th, if I put the 1 right here, that'll be the smallest power of 10 that exceeds 0 and 1500ths. So what is this as a power of 10? What is 0 and 1/10 as a power of 10? Go ahead and maybe think about what you would write here. And let's see if we agree. So I said 10 to the negative first power. So I'm putting the 1 right here in 1 decimal place behind the decimal point. And as we learned in our previous lessons, if we have a negative exponent, we can write that as the reciprocal of it in positive exponent form. So 10 to the negative first is equal to 1 over 10 to the first power. And anything to the first power is just 10. So the magnitude of the weight of a post-it note is 1/10, or 1 over 10 to the first power. Let's do one more. Again, I want to look at one that is represented by a small value. In the Physics Fact Book, published in 1999, it states that the diameter of a human hair, meaning the distance directly through the center of a human hair, is 0 and 254 hundred thousandths of a centimeter. Really pretty small. So we want to see if we can figure out the magnitude. So again, we need to find the smallest power of 10 that exceeds it. So basically, where can I put a 1 that is going to be the smallest power of 10 that exceeds 254 hundred thousandths. Think about that for a minute, maybe jot it down. Let's see if you and I agree. So here's what I came up with. 0 and 100th. So putting the 1 right there. Again, be looking at this pattern of how the place value of the magnitude compares to the place value of the actual number. So 0 and 100th is the magnitude, the smallest power of 10, that exceeds 0 and 254 hundred thousandths. So what is this expressed as a power of 10? Take a moment to think about that. Well, it would be 10 to the second power, because the 1 is 2 place values behind the decimal point, so we have to use a negative exponent. And 10 to the negative second power, or negative squared, would be 1 over 10 to the second power. And in its decimal form is 0 and 100th. So hopefully that gave us a little more practice, a little better understanding of magnitude. Take a moment to make sure your notes are fully complete, that you have the header copied down along with today's date, and all of our work here today. And if you want to go ahead and get a head start on the summary, that's not a bad idea either.